Hello again. My name is Mark, and I am an AI practitioner, an AI enthusiast, a tech leader, and formerly a director of engineering for a large Fortune 500 company. In November of this past year, Anthropic debuted their computer use API to the public in beta. From my perspective, this was a huge milestone as it's the first generally available autonomous agentic API. What does all that mean? Well, it means they released a model capable of complex real world task completion. So, again, this is a very big deal. Anthropic also created a framework to help developers get started. I've looked at it and it's opinionated in some interesting ways, such as giving agents access to the Bash shell or various desktop applications like spreadsheets. And so, before embracing their approach, I wanted to understand agents a bit more broadly. How do agents work? How do they reason? How do they choose the next best action from a menu of all possible actions? So, to that end, I embarked on a month-long technical challenge of actually building my own homegrown agent. This agent is very rudimentary, and I plan to build up its capabilities over time, but I wanted to understand agents more deeply and concluded that implementing a naive autonomous agent would be the most efficient path. And speaking of naive autonomous agents, I gave my youngest son $20 and sent him to the grocery store on a scooter to get some milk. So he comes back with neither the milk nor the $20. What a fitting analogy, as this is what we can probably expect from our early days naive autonomous agents. And at least my losses were capped at $20. All right, so let's talk about autonomous agents. What are they? Agent is already an overused AI buzzword, which in most cases simply means AI-enabled widget. So then, what's autonomous about it? Well, here's my definition. An autonomous agent takes a high-level goal as input, then breaks that goal down into actionable steps, then proceeds to execute those steps to achieve the goal, and when complete, provides a summary of the results, all without human intervention. So, to recap, high-level goal, actionable steps, execution of steps, summary of results, no human interaction. The remainder of this video, whenever I say agent, just know that I mean autonomous agent. All the way back in 1948, Claude Shannon, famously known as the father of information theory, built an electromechanical version of what might be considered an early autonomous agent. In his setup, a robot mouse was able to navigate a maze using simple trial and error. As it goes along, it builds up a mental model of the maze's solution using just 79 electromechanical relays, plus of course some servos and motors and a big electromagnet, effectively the innards of a pinball machine. And all this was mounted out of view under the tabletop. What a marvel of technical efficiency. The key idea here is that once the mouse learns the solution to the maze, it can effortlessly replay that solution. And if you reconfigure the maze, then the mouse must, of course, relearn the maze's solution. This is the essence of an autonomous agent. So let's extrapolate this to the real world. In real life, I hate to say it, but you are the mouse. And the maze that you're trying to navigate is probably Workday or ServiceNow or Concur or some other enterprise SaaS app. Wouldn't you just love to hand that off to an autonomous agent? Autonomous agents, in my view, are the killer app we've been waiting for, pretty much since SaaS became a thing. And at the current rate of improvement, fully independent autonomous agents are literally just over the next hill. Reasoning and recognition have so greatly improved that we can almost fully delegate tasks to these agents, confident in their ability to complete them successfully. Something else to consider is that these agents are going to be ridiculously scalable. It's going to be as if you're able to make 10, if not 100 clones of yourself. your own private swarm of minions onto which you can delegate all those TPS reports. Autonomous agents come in two flavors, naive and trained. A naive agent would be the rat navigating the maze for the very first time. A trained agent would be the rat replaying from memory the solved solution to the maze. The late physicist Richard Feynman once said, "What I cannot create, I do not understand." So to that end, I wanted to create my own autonomous agent to better understand its technical underpinnings. I've written up a use case describing how I would architect an autonomous agent to be able to service user requests. Happy to share that document if anyone's interested. Anyhow, here's what I came up with. Step 1. A user initiates a request. This is just the user's query. For instance, let's say that we wanted to find out how much a double burger costs at In-N-Out. For the uninitiated, In-N-Out is a burger chain, and the double means 2 meat, 2 cheese. It's their top seller. Okay, so that would be our user query. Step 2, deconstruct the request. This is where named entity recognition occurs to extract entities, proper names, and other such details. When I was in elementary school, we had to identify the who, what, when, why, where, and how of a given scenario. Our agent is going to need to do something very similar. Step 3, refine the request. This is where we would normalize the request, correcting things like spelling and punctuation errors, etc. Step 4, define the goal. The user's initial inquiry may contain the goal, or it may not. Either way, the goal, i.e. the stopping point, needs to be determined and made explicit. Step 5, echo the goal. This brings the human in the loop by giving them the option to accept or to refine or modify the query. Step 6, formulate a plan of attack. This is where we look to our model to formulate and articulate an action plan, described as a series of discrete, actionable steps. Step 7, perform a Google search. Believe it or not, this is a very efficient way to ground a search in terms of context, relevance, popularity, and so on, because it does a sort of pre-wash on the search criteria, further normalizing it. Step 8, assess search results. In the event the first search result contains the answer, then we're done. But in most cases, it does not. And this is where we would make that determination on whether to halt or continue. Step 9, initiate goal seeking. This represents the agent's reasoning loop. Anything more than a trivial search may require many recursive steps, and this is where that recursive drill down would occur. So, that is how I would naively structure an autonomous agent to process requests if I were to implement it from scratch. Fortunately, I didn't need to start completely from scratch. I came across the following white paper in which the authors prototyped an LMM-powered web agent that can complete user instructions end-to-end by interacting with real-world websites. I'll link to it. What's unique about their approach is that they leverage LMMs, which are large multimodal models, in lieu of LLMs, large language models. LLMs work only on text, where LMMs work on text, images, audio, and video. That's where the multimodal aspect comes into play. And it means that you can literally feed a screenshot of your current screen into the model for inference, and it will parse that screenshot and provide feedback on what it sees. Furthermore, you can prompt it to determine which next action it should take based on what it sees. This allows it to generate the plan of attack discussed earlier. And Web Voyager explicitly targets real-world tasks such as placing an order on Amazon or booking travel on Booking.com. In their benchmarks, they claim a 60% success rate executing their benchmarking test suite. Other frameworks have only mimicked autonomous tasks by benchmarking simulated web tasks only. So, that makes this even more impressive, and a lot of startups have taken notice. So kudos to these guys for pioneering such a novel and effective approach. Web Voyager was developed on OpenAI's GPT-4V model. This model has since been retired and its functionality rolled into GPT-4o. I chose to use Anthropic's model instead, so I retrofitted the scaffolding to work with Anthropic's Claude 3.5 Sonnet model. So let's see it in action. So what we're observing is the naive autonomous agent I wrote atop Web Voyager's scaffolding. It starts with the query, how much is a double-double at in and out? The query was fed in via JSON-L input file, which instructs it to begin on Google's search page. It proceeds to launch a web browser using Selenium's WebDriver. It overlays numbered bounding rectangles on each page, which are used to provide reference cues to the model. A screenshot is taken and sent to Anthropic for its analysis. Anthropic comes back with two things, a thought and an action. Notice that it reasons out loud, so to speak, articulating how it arrives at the next action. There are only 7 possible next actions. In this case, the next action is to type into screen element 7, say. This command is passed back to Selenium, which performs the operation, directing us to the next page. It applies the same procedure to unexpected pop-ups and is able to clear the dialogues and continue its chain of thought. What's ingenious here is that the model itself, via a process of reflection, is told to evaluate its own thought processes to determine if all the answer criteria have been met. Unfortunately, the agent fails on this run because it navigates to a non-authoritative website where it loses its train of thought. I had more success with DuckDuckGo. So what I've presented here is an extremely trivial example, but even though the example is trivial, it demonstrates the model's fundamental reasoning capabilities. And this suggests there should be no issues whatsoever in scaling this up to any arbitrary workflow, irrespective of complexity. Also, it turns out that my proposed agentic workflow isn't too terrible, especially when compared to the Web Voyager approach. The Web Voyager approach leverages the model itself to perform many of the steps I had broken out as discrete steps. For instance, deconstructing the request, refining the request, defining the goal, formulating the plan of attack, etc. All of these are handled implicitly by the model. In terms of grounding, initially, I thought that Google would provide the best factual grounding for user queries, and was surprised to learn that's not the case. The Google search homepage, unfortunately, has become overly cluttered, now including many elements irrelevant to search. Case in point, all the pop-ups. The search results themselves have also become a bit muddled. AI Overview often contains stale and superfluous data, in my experience. For instance, it's December 2024, and it's giving me results from June 2024. Also, the search results are not authoritative. For instance, for In-N-Out Burger, the In-N-Out corporate website should have been the top ranked result, and it wasn't. The net result is the agent is getting confused and traversing down various rabbit holes, all of which is computationally expensive. You're burning through tokens on this superfluous noise. So using Google for grounding would mean having to debias a lot of this noise, either in the prompt syntax or in the agent's code. Thank God for DuckDuckGo. It provides exactly what's needed, uncluttered, unbiased search. And because of that, it's able to get to an acceptable answer much quicker. Overall, I think results would further be improved by always automatically ascertaining the user's current geographic location and setting that as a default. Similarly, the time context should default to now, unless the user specifies otherwise. Dozens of test runs yielded results that were 80% identical. However, 20% of results were wildly unpredictable. The prime directive of an agent is predictability and explainability above all else. So some degree of hyperparameter or other tuning will be essential to reducing this variability. But overall, I'm quite pleased at what my modest demo agent was able to accomplish. All in all, a useful starting point. What's next? The overarching goal is to build an agent that does something useful. In subsequent episodes, the capabilities of this agent will be greatly enhanced so as to get us to that point. In future updates, I'll be tackling issues such as how to effectively sandbox an agent. An agent can be initiated from the desktop, yet must also interface with the Wild Wild West, which is the public internet, all without becoming a ransomware honeypot. So we'll look into solutions for that. So this is episode 1, and more episodes on this topic will almost certainly follow. So I'll end it here, and I invite you to come back for episode 2. Until then, so long for now.